In this lesson, we're going to learn about how solutions form. And one of the things that is worth noting is that we're going to describe it in a way that's not exactly how it happens. This is kind of like a stepwise process, or at least we describe it as a stepwise process, as if it happens in this way that's being described here. But ultimately, this is all very chaotic and it happens in a kind of non-structured pattern. So let's see what's up. So theoretically, dissolving can be described as three separate processes. So step one here. I'm going to highlight this just to show you that it's also got a bit of a picture to go with it. You're basically taking the solute particles and then separating them out. So as you can imagine, you're going to take these particles, which are sort of hanging out and doing its thing. They're all attracted to each other in whatever way they're supposed to be attracted, and then you're pulling them apart. Step two. You then take the solvent particles, so whatever intermolecular forces there are holding the solvent together as you form a solution. Those are then going to be pulled apart. They're just hanging out at first, intermolecular forces keeping them attracted to each other, but then now we're as if we're going to come in there and just sort of rip them apart so they have a little bit of space in between them. Right? The intermolecular forces are not really there. And then finally, in step three, we're going to take those two samples, right? The separated solute particles, the separated or expanded solvent particles, and then we're going to allow them to intermingle. So whatever space is there will now be occupied by either a solvent or a solute particle. And that'll be step three right here. That's when we kind of imagine this process occurring. It's not exactly, again, happening this way, but we can't really just sit there, separate the solute particles first, put them in a pile, and then take a second container of your solvent and go ahead and separate those particles, put those in a pile, and then when I'm ready, I can go ahead and put them on top of each other so they start forming a solution. Right. As you can imagine, of course, this is a very messy, non-straightforward, non-structured process. But this is how we can visualize it, so it helps us organize what might be considered in terms of energy. Before we move on to the actual energy parts, though, let's talk about how we can kind of determine whether or not two things will dissolve into each other. First of all, we're going to use a very, very simple formula, or a very simple statement anyway right here, is like dissolves like. That's going to be a pretty useful saying because that helps us predict whether or not two substances will dissolve into each other. But more specifically, when they say like dissolves like what, right? Similar what? Similar things dissolve other similar things. And really, it should be like polarities dissolve like polarities. So similar polarities will dissolve other substances that have similar polarities. So here's very specific examples. First of all, if you have a polar solute and a polar solvent, those are going to form a solution. Those are very likely to form a solution. At the same time, nonpolar solutes and nonpolar solvents, this should be solvents right here, right? That's going to end up having a solution, right? Likely to form a solution. So nonpolar, polar, and polar. That's what it means by like dissolves like. On the other hand, these are a lot less likely to occur when you have a polar solute and then a nonpolar solvent, right? And then vice versa, nonpolar solute and a polar, can't seem to type these out right, solvent. So those would not be likely to occur. Now, this is a general rule of thumb. As with any rules of thumb, there's always exceptions. But for now, just generally recognize if you see two things that are of similar polarities, they're going to be able to dissolve each other. So then, of course, we need to get into why this happens. So what is the exact nature for two substances being able to dissolve into each other? Well, when it comes down to, remember this third step, if you remember this conversation we had a minute ago, so this third step right here, right, where the particles then again come to interact with each other. Remember, that interaction is going to just have some kind of energy, whether it goes in or goes out. There's going to be some kind of energy change that occurs. And this energy change helps us sort of indicate whether or not the solvent and the solute will dissolve into each other. Now, again, this is all very much a general rule of thumb. So like I said, there's going to be some exceptions, but overall, right, this is the process that's generally key. What happens as these particles start to interact with each other, right? So let's use this color instead. So again, if you have these interactions from here to here, and here to here, here to here, here to here, so on and so forth, right? The solute and solvent particles, are those interactions going to be energetically favorable? Right? Are those interactions going to be a positive interaction, right? Something that's going to be good. Or on the other hand, is the interaction going to end up being maybe not so favorable? And how that works out, right? So let's say we have over here on the right side, these two particles, you have CH2Cl2, and you have this compound ethane, which has a formula of C2H6. Right, CH2Cl2. And these two particles, let's say we attempt to dissolve them into each other, right? We try to make these two to where one is a solute, one's a solvent, and then try to make them work out. eventually, right, when you have them interact with each other, you have to consider what's going on. This is actually a non-polar substance right here. It's non-polar. Over here on the right side, this is definitely a polar substance. So what's the likelihood of these two interacting in a favorable way? Not very, right? Because polar substances have a sort of dipole moment, right? In this case, it's kind of drawn that way. So this is the overall dipole moment for that molecule. It's polar, right? It's a slight negative on the outside here, it's slight positive towards the carbon. But on this side, this ethane molecule, there's no polarity. So there's no real attraction for there to be between a positive and a negative. So this would be an example of an interaction that's not really favorable. And so you'd actually expect these two to not really dissolve into each other. Again, like I said, generally speaking, this is a rule of thumb. If polar substances try to interact with nonpolar substances, they won't dissolve. Now, that's not to say, of course, in other contexts they won't react or do other things, but for now, the whole conversation is about whether or not these two will distribute evenly throughout each other. The answer would probably be no. Let's see an example of how this works. You have two different substances that you've spilled on the ground. One is grease, right? It's got that kind of generic formula of C20H42. That's represented by these molecules. And the potassium iodide, which is the formula Ki. All right, real quick as a reminder, potassium iodide is definitely an ionic compound, so we're not going to have a single molecule that can be used to represent it. You also have two liquid solvents, which are hexane, C6H14, represented by this guy, and methanol, which has a form of CH3OH, represented by this guy, available to clean up these spills. Right. So now you have your grease and potassium iodide; those are your solutes. Right. Those are the spills on the ground, and you want to be able to clean them off of a surface by putting a solvent on them, like potentially hexane and methanol. Which one's most appropriate to clean up which substance, and justify this answer? All right, so remember, the whole idea here is that when we take these substances and we're trying to clean them up, right, we're going to use something that can dissolve them so they can be picked up by some other rag or towel or whatever, so that it gets off of the ground. We want to remove it, and the best way to do that is to dissolve it into something which you can then wipe away. So when it comes to grease, right, this guy right here, it's all C's and H's, right? So what do we know about carbons and hydrogens is that they're generally nonpolar, and this entire molecule is all carbons and hydrogens, and so that's expected to be a nonpolar substance. Right, so that's my spilled substance that we need to clean up with a now non-polar solute. Well, when I compare hexane and methanol, if I look at methanol, right, this guy's got the O right here, that very highly electronegative O. This guy's going to have some hydrogen bonding. It's a polar molecule, but in addition, it has hydrogen bonding, which is very much not a non-polar thing. It's a very polar thing. On the other hand, hexane, the other potential solvent, this is going to be C6H6, right? This is all C's and H's, and that's going to be all non-polar. And so, which one's likeliest to be a better, or which one's going to be, anyway, between methanol and grease? Which one of these two is the better solvent to wipe up grease? Hethane and hethane versus methanol, the answer would definitely be hexane. All right, so hexane is the better one to clean up grease. When it comes to potassium iodide, right, this one then, looking at methanol, we'd already determined that this is a very polar substance. And iodine, right, potassium iodide, this is an ionic compound that has lots of positives and lots of negative, very obvious charges. So the methanol, the polarity of methanol, right, which has some slight positive, slight negative, that can be attracted to the very positive, very negative ions of potassium iodide. And so, in terms of the appropriate solvent here, methanol would be the appropriate one to pick up potassium iodide. Now, again, potassium iodide, you're thinking maybe, oh, that's not exactly a molecule, right? And the important thing, though, ultimately is whether or not they have similar positive, negative abilities, right? When I say like dissolves like, we're saying like charges or things that have charges or things that have polarities will be attracted to something else that has polarities. In this case, we're kind of taking the polarity to an extreme, which would be like an ionic bond. Other applications here to consider, for example, sometimes you may have heard of like these hydrophobic water sprays, which you see applied here. Say you have a boot, and the boot, of course, the fabric is usually some kind of leather. That can soak up a lot of water, but if you were to spray it with this hydrophobic coating, right, this very, very oily, non-polar coating, that would actually allow it to keep water out. A lot of times you also see shoes, other leather shoes that are formed this way, that typically have this sheen or this very, very specific coating on there because they're hydrophobic or they're oily or they're non-polar. Lots and lots of carbons and hydrogens involved. And so polar water, right, so you can see the little droplets here, all that polar water or again, more appropriately, water that has polar properties, that can't really dissolve or penetrate that surface. So it actually protects the leather or protects whatever fabric is protected by that layer of oily coating. WD-40, similar process, the water displacement method, 40th formula, hence WD-40. This again is containing a lot of nonpolar substances that can dissolve other nonpolar substances. So if you kind of have some, like, some sort of a joint or some sort of a gear or some sort of mechanical object that requires it to have smooth sort of movement anyway, you can use a little bit of WD-40 to kind of loosen it up, because it pushes out any potential water that gums it up, so that the oil and the greases that are already present, those can again allow you to move past each other. But you don't need too much, because honestly, since it is a non-polar substance, that can dissolve the present oils, the oils you want to have there. That can dissolve away the oils, so that now the oils will be off of the chain or the gear of whatever you wanted to function, and it kind of makes things worse. So just use a little bit of WD-40. You don't want to overdo it. And of course, removing sticker residue. Sometimes you experience this when you have a surface that you remove a sort of label or UPC code or something like that. And then of course, there's a bunch of that crud that gets left over on there. Well, again, that a lot of times is glued on there with some sort of organic substance. And when I say organic, again, we're talking about carbon and hydrogen substances, lots of carbons and hydrogens. And so if I know something has lots of carbons and hydrogens, typically it's going to be non-polar. And therefore, we can use something that is non-polar to help wipe that off. So that might mean maybe perhaps some cooking oil. Right, that's pretty terrible line. So non-polar solvents anyway, like cooking oil, olive oil, vegetable oil, again, they're all some kind of oil, which are all non-polar. And because they're non-polar, they can dissolve these non-polar, generally speaking, organic glues, which you can then again remove, so you don't have that little unsightly sticker on that surface anymore. A couple other terms here. When two substances can dissolve each other, they're described as soluble. And then specifically, or you can see the examples here, sugar is soluble in water, or you can say olive oil and grease are soluble. But when talking about fluid solubility, a lot of times we use the word miscible or immiscible. Miscible is where two liquids are soluble. Immiscible is where two liquids are insoluble. So olive oil and water, right? All water and oil don't mix. Again, that's just a casual way of saying that the two are actually immiscible. A couple other factors that affect solubility. We'll cover a couple of them. First of all, let's talk about the structure effects. So what exactly is the composition of these molecules, and how does that affect solubility? Let's use something like vitamins as a way to illustrate this concept. We'll look at the visuals in the next slide to help you make more sense of it. But there are two main categories of vitamins that most people use to categorize. The first one is fat soluble. Right, so think about what fat is composed of, right? Lots of non-polar, lots of carbons and hydrogens when it comes to lipids and such. So yeah, it's going to be fat-soluble vitamins. A, D, E, and K, vitamins A, vitamins D, E, and K. And then you also have water-soluble vitamins like vitamin C and B. And yeah, for those of you who might know anything about B, there's like so many varieties of them. There's not just one single B. But, like we said here, fats are primarily made of long chains of carbons and hydrogens. These lipids are lots and lots of non-polar substances. And so that's why vitamin A dissolves well in fat, but vitamin C doesn't. And so the good thing about that is that vitamin A can be stored in fat for a long period of time, right? They can usually stay for a little while, so you don't have to constantly intake some substances that have vitamin A. But the problem is, too, if you take in too much vitamin A, right, that means your body stores way more vitamin A than it needs. And as with almost anything, if you have too much, it's always generally a harmful thing. And so the structure here is what we're looking at. So these are two diagrams here of each molecule. Vitamin A on the left side here and the vitamin C on the right side here. Let's take a look at vitamin C because it's a little more compact. And something you'll notice here is that you've got lots of O's, you got lots of big red O's, and the hydrogens bonded to them in this structure. But also down here in this sort of drawn out Lewis structure, you see a lot of O's and H's as well. Right? In this case, it has 5 of them, all of which are pretty compact. And again, they're all more or less right in that molecule. And that makes it pretty polar, right? Because you do have lots of these hydrogen bonds that could potentially, or these OH bonds anyway, that could potentially make it polar. And as a result, it's going to be very soluble in water. On the other hand, you have vitamin A here on the left side, right? Vitamin A, if you notice, there's only like one little bit of oxygen and hydrogen here, right? Kind of represented by this guy down here as well. That's one little bit of polarity. But then if you look at the rest of the molecule, the huge majority of the molecule on the left side here, those are all the C's and H's that you expect from a polar or non-polar substance. And because it's so non-polar, right? All of this stuff out here, all these C's and H's, it's so non-polar that, we typically don't see it being dissolved in water very well. It gets dissolved, potentially gets is very fat soluble, very lipid soluble. So that's why it typically gets stored. So that's basically how, again, we can look at their structure and generally know if it's going to dissolve or not into a solvent. That'll do it.